Hello everyone, I am Anukriti Sethi, a fourth year engineering physics student from IIT Roorkee. Today I am presenting on chaos theory, specifically focusing on its applications in signal processing. Chaos might sound like complete randomness, but it's actually about finding patterns in unpredictable systems, something that plays a big role in fields like communication and control system. Let's start by looking at what chaos theory really means. So, I'll be covering the following key points during my presentation. Let's begin with introduction to chaos theory. Chaos theory studies dynamic systems that are incredibly sensitive to their starting conditions, a concept often referred to as the butterfly effect. This means small changes at the start can lead to vastly different outcomes. This theory was first used by Edward Lorenz but has since been applied across many fields, including signal processing. In chaotic systems, signals are controlled by nonlinear equations. Even though these systems are deterministic, meaning they follow specific rules, they are difficult to predict over time because small changes can have a huge impact. This is very different from random noise because chaotic signals have an underlying structure, but it's still sensitive to small variations. In signal processing, chaos can appear in systems used for communication, control, and remote sensing. Chaotic behavior in these systems comes from nonlinearities and feedback loops, making their behavior unpredictable. These systems defy the usual classification based on properties like linearity or time invariance, but they can still follow deterministic rules. For example, feedback loops in control systems can cause chaotic behavior, which makes stable system design very challenging. This is also seen in satellite communication and radar systems, where small nonlinear changes can lead to chaotic interference and distortions in signal transmission. Moving on to classification of signals, a deterministic signal is a signal whose behavior can be precisely predicted based on a known mathematical function, while a random signal is a signal with unpredictable behavior lacking any pattern or structure. But chaotic signals don't fit neatly into either. They are deterministic but appear random because of how sensitive they are to initial conditions. Basic operations like scaling or time reversal also affect chaotic signals differently because of this sensitivity. Even simple signals such as sinusoidal waves can exhibit chaotic behavior under the right conditions, such as in circuits with nonlinear components like diodes. A good example is when damped signals become chaotic in forced damped oscillators, a concept used in electronics. Moving on to convolution and impulse response. Convolution is a key tool in linear systems used to predict system output by combining input with its impulse response. But in chaotic systems, impulse responses are far more complex due to their nonlinear nature. A small change in the input can result in large, unpredictable differences in the output, making traditional convolution methods unreliable. In chaotic systems, we often turn to other methods like Lyapunov exponents to describe how chaotic signals evolve. This unpredictability is particularly challenging in secure communication systems where filtering chaotic signals can be difficult. Now, coming to Fourier representation, the Fourier transform is commonly used to break down signals into their frequency components, but chaotic signals present unique challenges because they don't have well-defined frequency peaks. Instead, they exhibit a broadband spectrum, meaning their energy is spread across many frequencies. This makes chaotic signals appear noise-like, making it difficult to extract meaningful frequency data. However, this property can be useful in applications like secure communication, where chaos-based modulation techniques help mask signals, making them harder to detect or decode. The Laplace transform is a useful tool for analyzing linear systems in the frequency domain, but it struggles with chaotic systems due to their nonlinear behavior again. Chaotic systems often have unstable and complex poles that makes prediction difficult. For example, in circuits like Chua's circuit, Laplace transforms can be useful in the initial linear stages, but once chaos sets in, other nonlinear methods must be used to fully understand the system's behavior. Now, looking at chaos in discrete time systems, that is Z transform. Chaotic behavior isn't limited to continuous systems. It can also appear in discrete time systems, which are analyzed using the Z transform. The logistic map is a good example of how simple iterative processes can lead to chaos. In digital signal processing, chaotic sequences generated by discrete time maps are used for applications like secure communication, where pseudo-random behavior is needed to make signals harder to reverse engineer. Applications of the chaos theory. Chaos is increasingly being used in secure communication systems. By using chaotic signals to mask data, these systems become much harder for unintended receivers to decode. Traditional modulation techniques like amplitude and frequency modulation behave differently in chaotic systems, which makes them ideal for encryption purposes. Chaos-based spread spectrum techniques take advantage of the broad spectral characteristics of chaotic signals, making them useful for secure data transmission across wide frequency ranges. It is used for many applications, such as in weather forecasting, where ensemble forecasting methods use chaos theory to generate a range of possible weather scenarios. It is also used in secure communication, where spectrum communication and chaos based encryption algorithms are used. In biology and medicine, there is also application of chaos theory. For example, ECG signals often exhibit chaotic behavior, and understanding these can help in diagnosing heart diseases. For economics and finance, stock market analysis and modeling unpredictable economic cycles, chaos theory can be used. There are several other applications in robotics and control systems, in astronomy and space science, in ecology and population dynamics, in psychology and cognitive science, and much more. Although chaos has many useful applications, it also poses challenges. Chaotic signals are unpredictable and spread across a broad spectrum, which makes them hard to analyze, filter, or control. This creates difficulties in real world systems where stability is important. However, ongoing research is looking at ways to harness chaos for secure communication, noise reduction, and encryption. In the future, chaos based systems may play a significant role in technologies like 5G and beyond. To wrap up, chaos theory plays a crucial role in understanding and managing complex systems, especially in signal processing. Although chaos adds unpredictability, it also opens up opportunities, particularly in communication and encryption. As we continue to advance in technology, chaos will remain an important tool in dealing with non-linear complex systems. Thank you for your attention throughout my presentation.